You can get off. You can go down. There we go. Oh, yes. You do not resemble your name, Gracie. You are not graceful. Okay, guys, where are you at? Make sure I'm in there. I'm in here. Zoom, zoom, zoom. Okay, it's here. Okay, at least I know that you received the email.
Hey, Professor.
Hi, how you doing?
I'm doing well, I guess.
What happened, Gabe?
I have no clue. Honestly, I had no clue. I studied, I looked at the study guide. I did everything. I mean, I have no clue.
I mean, I could, if you want, I could stay a little bit after class to go through it with you, but literally speaking, Gabe, overall, I had a 71% average on it.
Yeah,
And
I don't know what I did.
If I dropped two tests took me from a 75% average down to the 71.
Oh, wow.
So I don't know what happened to you, but it wasn't a pretty sight, guy.
I know.
Make it up. We'll make it up on the next one.
Yeah. Yeah, my dad's like the final. Yeah, my dad's making me study from now. He made me write like a chemistry plan. Every chapter I'm gonna go through. And I don't know if you know, but my mom's a chemist. So my mom's like, yeah, I should tutor you, whatever. You should come to me for help. So,
well,
I'll just be, guess making my plan for the final to get an A.
Where we're going from here, a lot of the stuff we're going to do in the next couple days are stuff you've already had. We're going to do Lewis dots, and we're going to do Vesper, stuff you've already had. Now there's going to be some wrinkles that we put into it, but it's stuff that you've already had. All right. This may be a solo appearance because you seem to be the only one that's in today.
That's good. More practice and I guess for me.
That sounds good. That sounds good to me. And I've only got 2 participants. So we're going to get started because I got to get going through some of this stuff. All right.
All righty. Sounds good.
So I need to share screen. And a lot of what I'm doing right now is going to be stuff. Oh, somebody just popped in. Kevin just popped in. Kevin's kind of in the same boat as you are right now. Okay, from current slide. Okay, Kevin, you out there?
Oh, yeah.
We got a meeting of 2, okay? What happened to you, Kevin?
What do you mean?
You didn't do as well on the test.
No, I know. I've had a personal thing this last week, so I didn't really get time to study, and then I didn't really do the lab either, so.
Well, I mean, life intercedes with this stuff, and you guys get to drop one test, it gets replaced by the final, so don't get too discouraged, all right? As I was just telling Gabe, what we're going to be doing over the next couple of days, right now, I'm going to go through some periodic trends, then I'm going to get into Lewis dots today. You've done Lewis dots in intro. Then once we do Lewis dots, we're going to get into Vesper. Now, within, I think, maybe even next week is the Vesper lab. So on Tuesday night, after I go through some Vesper stuff, we're going to go through and hit on that heavily. Okay. Good morning, Jasmina.
Good morning. How are you?
I'm doing fine. Good job, Jasmina. Okay, as I
Thank
was
you.
telling guys, I do have a Dropbox for extra credit. It's worth 5 points. So if you want to do it, it's there. It is a rather difficult problem. It involves one of those problems that has the overall reaction, the Hess's overall reaction, and then the 3 other reactions that you got to manipulate to get the overall reaction. So that's what the extra credit quiz is about. Okay. Now, we're going to get into periodic trends here in a second. And this is a little more detailed, involving some things that quantum mechanics can explain. All right, first thing we're going to deal with is the effective nuclear charge. If you have an electron that's way out here, okay, doesn't it have some electrons between it and the nucleus? Doesn't it? Aren't there some inner electrons?
Yes.
So if there are inner electrons, don't the inner negative charges kind of absorb some of that positive charge that comes from the nucleus? Like if
Yeah.
there is one electron that's floating way out here by itself, and I got 10 electrons between it and the nucleus, then what's happening is those 10 electrons are kind of sucking up 10 of the positive charges from the nucleus. Does that make sense, guys?
Yeah.
All right. The other thing you have to realize is that when you have electrons that are in the same shell, they have the same charge. So what's happening is they're repelling each other. They want to get as far away from one another as is possible. Come on. So the core electrons are going to shield the attraction of the nucleus from the other electrons. And basically, a lot of the properties, a lot of the periodic trends that we're dealing with are determined by this effective nuclear charge. And basically, you can find this out by subtracting the inner electrons from the number of protons you have. Okay, if I have potassium, potassium has 18 inner core electrons and 19 protons. So the effective nuclear charge is going to be the 19 minus the 18 or a +1. Remember, it's just a crude estimate. And basically it underestimates because those electrons that are inside can't perfectly shield that outer electron. There are kind of like spaces between them that the outer electron can feel the inner nucleus protons. So what the first periodic trend we're going to get into are the sizes of the atoms. And basically, the bonding atomic radius is 1/2 of the distance between the covalently bonded nuclei. So if I've got a total distance of d, the bonding radius is going to be 1/2 d. Basically, we're saying, okay, the outermost electron for the right atom is right there. The outermost for the left is right there, and that's going to be half the total distance. As we are doing, this isn't changing. As we are going from left to right, due to the increasing shielding effect, as you're going from left to right, the radius decreases. So the ionic size is going to depend upon the nuclear charge, number of electrons, and the orbitals in which those electrons exist. So if I'm dealing with lithium as opposed to sodium, I'm going down the chart. As I'm going down the chart, I'm adding another layer of orbitals where that final electron is located. So as I'm adding more and more orbitals, the size is increasing. Size increases going down the periodic table. Size increases going right to left because effectively you have less protons. Cations are smaller than their parent ions. This makes sense because if I've got a sodium atom, I have an extra orbital with an electron floating out there. If I make the sodium a cation, I take that electron away. When I take that electron away, I take that orbital away. It shrinks it down to the next orbital. So cations are smaller than their parent atoms. However, anions are larger than their parent ions. And what happens here is that if I have a neutral fluorine, I add one more electron in there. Electrons repel each other. Since they repel each other, they're going to want to get further and further apart from one another, which means that their effective size is going to increase. Cations are smaller than their parent. Anions are larger than their parent. When we have an isoelectric series, the ions have the same number of electrons. By that, I mean, if I have lithium, that's a +1. Bad caption here. If I have sodium, that's a +1. It has the same electron configuration as oxygen -2, which has the same electron configuration as magnesium +2 or fluorine -1. Does that make sense to you? Because
Yes.
if I'm dealing with magnesium, magnesium has lost those 2 electrons in its outermost shell, making it seem like neon, electron configuration wise. But if oxygen gains 2 electrons, it's also going to appear like neon's electron configuration. I'm going through this rather quickly, guys. If you're not understanding something, yell at me, okay?
Got it.
Now, ionic size is going to decrease with an increasing nuclear charge. That only makes sense because you got more positives in the center. Arrange. Get out your periodic table, and actually I gotta get mine out too because I gotta figure this out. I got chlorine, potassium, selenium, rubidium, and germanium. Which one is the largest one?
Rubidium?
Rubidium, yes, because it has electrons in the 5th orbital, the fifth principal quantum number. So rubidium is the largest. Okay, what would be next? Which 2 atoms are on the same principal number? Next one up, 4.
Potassium and selenium?
Potassium, selenium, and?
Germanium.
So all 3 of those. And what did we say going from left to right? Did they get bigger or did they get smaller?
It decreases, so it would go potassium, germanium, selenium.
Any argument, ladies and gentlemen?
No.
So what does that leave us, Cassidy?
Then chlorine's the smallest.
Chlorine is the smallest. Okay, Gabe. Do you remember what we said about the cations and anions?
And it like as
Do cations increase or decrease the size?
decrease.
Decrease. Cations decrease. So which one of these bottom ones do you think is the smallest?
N+3.
Okay. What about the next one?
N+1.
Next one?
N. And
Then-
then N-2 and then N-3.
Are we going this, guys? We understand what we just did.
Yeah.
Yeah.
All right. Flipping to the next periodic trend is something called ionization energy. And ionization energy is the amount of energy that is required to remove an electron from the ground state of an atom or ion. Okay, notice that's atom or ion. If we have magnesium, we can take one electron away. If we take one electron away, we make magnesium 1+. Then we have a second ionization energy to take that second electron away. They're different. They're different because the circumstances are different. First is the energy required to remove the first electron. Second ionization energy is the amount required to remove that second one. Now, do you think it's harder to remove the first or the second electron?
The second.
Why?
The first one is blocking it from the nucleus.
Kind of, sort of, Kevin. Kind of, sort of. Remember the effective nuclear charge, okay? When you have that second electron being taken away, you're already dealing with a positive ion, okay? It's an inexact amount of charge that is on that ion. So you have a positive charge, it's harder to take it away. If you have a magnet that's twice as strong as a second magnet, the one that's twice as strong is going to be harder to pull away from iron than the one that is weaker. Does that make sense to you? By adding positive charges there, we make that magnet that's called the atom stronger. So if we're looking down here, okay, each time we take another ionization, it takes more and more energy. Do we see that? Each time you take that next electron away, for example, aluminum, I take the first one away, no problem. That's only 578. I take the second away, that's 3 times what the first one was. I take that third electron away, and it is 5 times. Each electron you take away from an atom takes more and more energy to take that electron away. Now, let's look at this. Wow. To go from the first one of sodium to the second. Think quantum mechanics here, guys. To go from the first ionization of sodium to the second. Look at that jump. That's 10 times. Look at magnesium. To take the second away from magnesium, that's only a 2 times jump, right? And yet, when I go from magnesium second to third, whoa, I'm jumping that about five times. So the first one was only 2 times. The second one was 5 times. Thinking in terms of quantum, why do you think that you have this big jump here? Do you remember what I said about filled shells and half-filled shells? What did I say about filled shells of electrons, filled orbitals, and half-filled orbitals? Come on, guys. I know all this stuff didn't float out of your head.
Is it just so that the orbital's filled all the way?
What does it in terms of stability, Cassidy? Would you
So
rather
that
have a filled
a
orbital or a half-filled orbital?
filled one?
Think of what's happening here. If I'm doing the electron configuration of sodium, it is 1s2, 2s2, 2p6, 3s1. If I lose that one orbital, right? I lose that one electron, I still have a filled p orbital for sodium, don't I?
Yeah.
But if I try and take that one electron away from the p, have I destroyed that filled orbital?
Yes.
Have I destabilized it?
Yes.
So it takes more energy to take, going from taking it off of the 3s, taking one electron away from the 3s takes less energy than taking one out of the 2p, because I'm destroying a completely filled orbital. Does that kind of make sense, guys?
Yeah.
Look what's happening with magnesium. Magnesium has 2 electrons in that s orbital. Okay? So it's going to take more energy to pull one out of that p orbital than it's going to take it out of the s, the 2 out of the s. You look at aluminum. Aluminum has, look at this, guys. It takes less energy to take an electron away from aluminum than it does to take one off of magnesium. But aluminum has more protons. How do you explain this? You explain this because the first electron coming out of aluminum is coming from the 3p orbital. It's just got one electron out there, guys. It can lose that in a heartbeat to make a filled 3s orbital. So that's why aluminum's ionization energy, first ionization energy, is less than that of magnesium. Then looky here. Look at aluminum. You've got a filled s orbital going from the first to the second ionization. You got a filled s orbital. So it takes about 3 times as much energy to get the second one out of there. But going from the second to the third, it only takes about 1.5 times as much energy. This is all explained by the quantum mechanics. When you're going in aluminum, the first one you're taking out comes from that p orbital. I still have a filled s. So if I'm aluminum, I'm still somewhat happy. Then you go and try and take another electron away from a filled orbital. It's going to take more energy to get that away. Now I've got 2 electrons gone. I still have 1 electron in that s orbital. Aluminum, I don't need that one. So it's going to take a little more energy to take that third one away, but less than the distance it took from you from the first to the second. The jump from the first to the second ionization is much greater in aluminum than from the second to the third. Is that making sense to you guys?
Yeah.
Okay. As you go down a column, less energy is required. So what I mean by that, lithium, you only have for lithium, you have the inner 1s and you have that 2s. It's real close to the nucleus. So it's going to take, it feels more of that positive charge than something like cesium, which is down to the 6th s level. Cesium doesn't feel as much of a positive charge as that electron in lithium. So as you're going down the periodic table, the ionization energy gets less. It's easier to remove that first electron. Again, we're talking about the first electron at that point. Generally speaking, as you're going across the periodic table, it gets harder to remove an electron because you have more protons. There's more Z effective increases as you're going from left to right. But looky here. Sorry, let me go back. Previous. Looky here, you go lithium, then beryllium. It takes less energy to take an electron out of boron than it does out of beryllium. Are you seeing this? Why do you suppose this is? Guys, I just given you the answer a few seconds ago.
Is it because it's a halogen?
No, we're talking this one. This one is beryllium, Be.
Mhm.
Okay. The next one, remember, we're going across this way. We're increasing the atomic number. So we've gone from beryllium 4 to boron 5. And it takes less energy to take an electron away from boron than it does to take it away from beryllium. Look at your periodic chart, guys. Why do you think this occurs? Okay, I'm hearing little crickets here. What can you say about the orbitals of beryllium? Are they completely full?
No.
Beryllium, Be,
Oh, sorry.
Cassidy?
Yeah. Sorry. Wrong. Looking at the wrong B.
So beryllium has completely filled orbitals. What about boron?
It does not.
So,
Oh, okay.
so does that explain why it takes less energy to take it away from boron than beryllium?
Yes.
All right. Let's look up here. We go from boron. It makes sense that carbon takes more energy. This one is carbon. Nitrogen, it takes more energy. Then we get to oxygen. The energy goes down again. Remember what I said about the stability of full orbitals and half-filled orbitals. Look at oxygen. What has happened to oxygen?
It's a half-filled orbital.
No, not oxygen. Guys, I want you to draw an orbital diagram of the p electrons for oxygen and the p electrons for nitrogen. Have we got that done, guys?
Yes.
Cassidy's done it. Jasmina, Kevin, Gabe, have you done it yet? I'm waiting to hear back from you guys.
I'm a little confused.
Gabe, What I just asked you to do is do an orbital diagram of just the 2p orbital for nitrogen and oxygen. Gabe, how many suborbitals are there in a p orbital? Somebody help them. How many orbitals?
6.
Not 6 orbitals. 3 orbitals. Each one of the orbitals has 2 electrons in it, possibly.
Okay.
All right. So we have 3 orbitals, 3 suborbitals for the p. For nitrogen, how many p electrons does it have?
3.
3. So for 3 orbitals, I get each one of those orbitals filled with 1 electron. I have a stable environment, right?
Yes.
All right. Now for oxygen, I got to shove another electron in somewhere. Where's it going to go?
Into the first orbital.
Okay. What's already in there?
Another electron.
Okay. Cassidy, do you have a brother or sister?
I have 2 brothers.
Did you ever get shoved in the back seat of the car and go on a long trip?
Every time.
All right. So if you're in the back seat, how soon after your father left the driveway, then the first "he's touching me" comment come?
Pretty quickly.
So if you've got 2 electrons in the same orbital, are they going to like it?
No.
So is oxygen really going to want to hang on to that extra electron?
No, it's unstable.
So therefore, it's easier to take an electron away from oxygen than it is from nitrogen. So what we're looking for, guys, when we're looking for the discontinuation of the trend, remember the trend going from left to right is that it becomes left to right becomes harder to take an electron away because you got more protons in there. Okay, going left to right. There are going to be 2 times going left to right when we're dealing with S and P orbitals that there is a strangeness to this trend, that the trend doesn't hold true. And that occurs when we're going from S electrons, S filled orbitals to the P, like going from beryllium to boron, going from magnesium to aluminum, calcium to gallium. That is all going to change because of the fact that for the S's, we have a filled orbital. Adding another electron into another orbital, it doesn't really want it. So it's going to be easy to pluck that electron away. The other instance is when we have a half-filled orbital. So if we're talking, there's a stability for the nitrogen, phosphorus, and arsenic, so that it is easier to take an electron away from oxygen, sulfur, or selenium. Is that making sense, guys?
Yeah.
It holds really true, guys. It really holds true for especially the second and the third shell. You can see that demonstrated here. It goes a little bit kaflooey with the fourth, and there's a major problem with the fifth. And basically what's happening in the third and the fourth is you're getting complications from more electrons being in that situation. Like, for example, if you have chromium, remember we said that we could take one away from the 4s to add to the 3d to make the 3d5 a half-filled shell. Do you remember that, guys? Do you remember I said when we were doing electron configurations that there was a problem going from chromium because chromium would like to have that D shell half filled. So it promotes one of the S electrons. Do you remember that?
Yes.
Yeah.
So if you look, what I just told you holds true a little bit, but there are complications because of that. So in the case of chromium, it becomes a little harder to take away that electron because it's kind of happy with its two half-filled shells. On the other hand, iron wants to get rid of its to get a half-filled shell. So there are complications going on there. Remember, general rule going left to right is that the ionization energy increases going left to right because there's more effective nuclear charge. But there are these anomalies. Look, we're going from beryllium to boron, energy goes down. Going from nitrogen to oxygen, energy goes down. Magnesium to aluminum, energy goes down. Phosphorus to sulfur goes down a little. Is this making sense, guys?
Yeah.
Yes.
So that is why when you get to an end of an orbital, you have that astronomical leap. What am I doing? How am I going backwards? Okay. All right. A new property. This one is called electron affinity. And the electron affinity is the energy exchange that occurs when you add an electron to a gaseous atom. Chlorine would rather be Cl2. So if it sees an electron out there, it's going to grab it. And when it grabs it, there's going to be a subsequent energy change. In general, as you go from left to right, electron affinity becomes more exothermic because as you go towards the right, what you're doing is you are getting closer to filling an orbital. Okay? There again, you have two discontinuations in the trend. Okay? Go between lithium and beryllium. Remember, we're trying in electron affinity, we're trying to attract electron. Ionization potential, we're trying to give up that electron. So for electron affinity, what is happening is we are trying to gain an electron. And look, beryllium, if it gains another electron, it fills an orbital. So it's going to be more exothermic for lithium to gain an electron than it is for beryllium. Beryllium, if it gains an electron, it's got one in now the p orbital. Again, if we're dealing with carbon versus nitrogen, if carbon gets another electron, I've half filled my p orbital. I'm happier. But if nitrogen gets an extra electron, it's got to put that extra electron in the back seat with its brother. So if it puts it in the back seat with its brother, that is not a happy situation. So it is more endothermic for nitrogen to grab an extra electron than it is for carbon. Again, it's the same logic that we use for the ionization potential. The difference is, in this case, for electron affinity, we're gaining an electron. For ionization potential, we're trying to lose one. Have I completely lost you guys? Or is this kind of making sense to you?
You lost me.
All right, Gabe. Gabe, would you agree? Would you agree that filled orbitals and half-filled orbitals are more stable situations?
Yes.
Okay. If I have lithium, remember electron affinity, going back here, electron affinity, I'm gaining an electron, right, Gabe?
Right, correct.
Okay, so if I am gaining an electron, if I'm gaining an electron, if lithium gains an electron, does it fill its S shell?
Yes.
But if beryllium gains an electron, does it have to shove one in its p orbital all by itself?
Yes. Yeah, it does.
So does that kind of destabilize the situation? Because I got this electron just floating out there by itself. Whereas for lithium, I got a filled electron, I got a filled orbital. Gabe?
Yeah. I don't know.
Okay. Gabe, stay after class. I'll go through it with you again. Kevin, Jasmine, and Cassidy, are we good with this? Do we understand what's going on?
Yes.
We good? Jasmina, Kevin? Kevin?
Yeah, I'm good.
Kevin?
I'm good.
Okay. Because if you're not good, stay after class with me and Gabe, all right? Because I have to get on. I have to get through. I have to get through Lewis dots here. We have another trend called electronegativity. And basically, it's the ability of an atom to attract an electron to itself. It is a relative scale. Again, because the atoms on the right side of the periodic table want to fill all their electrons out, fill out all their shells, the electronegativity, as a general rule, going from left to right, increases. Because we're getting further and further out as we go down the periodic table, electronegativity decreases as you're going down the chart. Are we good with that, guys?
Yeah.
Again, I'm going to go through it with Gabe at the end of the period. We're going to try and get this solid for Gabe. All right. If you are having troubles with this, let me know and continue on at the end. Right now, we're going to get into first lattice energy, and then we're going to get into, nope, that's not where I want to be. Stop share. No, where's my, it's all right. Just a little technical problem. We will deal with this in a second. Yeah. Where is this at? There we go. All right, now we're getting into chapter 10. Nope, and show from the beginning. And what we're going to do in chapter 10 now is we're going to talk a little bit about lattice energy and ionic compounds. We're going to deal with covalent bonding and get into Lewis dot structures. Then from there, we're going to get into electronegativity and polarity, resonance and formal charge. And the last thing we're going to get into here, I'm sorry to say, we're going to do more thermochemistry. We're going to deal with bond energies. So when we're dealing with ionic bonding, we're dealing with electron transfer. I'm sorry, I just lost my presence of mind there. When we're dealing with the ionic bonding, the electron actually gets transferred from one atom to the other. And we saw that this is a endothermic process. It takes energy to take an electron away from a particular atom. But we get that energy back if we take the electron away from one thing and we give it to another thing. We get some of that energy back when we're dealing with giving that electron from sodium to chlorine. But if you put sodium metal in with gaseous chlorine, it is almost an explosive reaction. We're dealing with a positive 495 to take the electron away from sodium, and we're getting 395 back by giving that electron to chlorine. That's an endothermic. If we add positive 495 with a negative 395, that's an endothermic reaction. It doesn't explain why, when you put sodium next to chlorine, they have this explosive reaction. There's a third piece here, guys. Taking that electron away from sodium, endothermic, gaining an electron, exothermic, but it's not enough to overcome this. There's a third piece. There's an attraction between the positive of the sodium to the negative of the chlorine. So because there is that attraction of the positive to the negative, that's more energy that gets released. And because there's more energy that gets released, that makes this reaction almost explosive. That third piece of the energy is called the lattice energy. It's the energy required to completely separate a mole of the ionic compound into its gaseous ions. In other words, if I have a mole of sodium chloride, lattice energy is the energy required to take that mole of sodium chloride and keep it splitting up to its individual sodium ions and chloride ions. This energy is associated with something called Coulomb's law. You are not going to have to work any mathematical problems with Coulomb's law, but I am going to require you to answer some questions on Coulomb's law. Coulomb's law says that the energy, the lattice energy, is equal to a constant times the charge on one of the particles times the charge on the second particle divided by the distance. Jasmina, do you have your periodic table out? Jasmina, do you have access to a periodic table?
Yes, I do. I have it in front of me.
Okay, now, if I tell you I have sodium chloride and I tell you I have potassium bromide, we got that?
Yeah.
Are the charges different? What's the charge on the potassium and the sodium? Come on, Jasmine. The potassium and sodium, what's the charge on them?
+1.
They're
Sorry.
both +1. What about chlorine and bromine?
Or 0. I mean,
Chlorine and
-1. Sorry.
chloride and bromide?
-1. Sorry.
-1. So in both instances, don't I have a charge of +1 and a charge of -1?
Yeah.
All right. So does that change from sodium chloride to potassium bromide?
No.
No. So my Q's are going to be the same. On the other hand, which one is larger? Which molecule is larger, sodium chloride or potassium bromide?
Sodium chloride or
Jasmina,
potassium
as you go
bromide?
down the periodic table, does that make the atoms bigger or smaller?
Bigger.
So again, I ask, is the distance between the sodium and the chloride bigger or smaller than the distance between the potassium and the bromide? Which one's bigger?
The potassium bromide.
So does that make the distance bigger?
Yes.
So what happens to the energy? What happens to the lattice energy? Does it go up or down?
Up.
If I'm dividing by a bigger number, Jasmina, does the energy go up or down?
Down.
The energy goes down. So the lattice energy for potassium bromide, because it's a bigger molecule, is less than the lattice energy between sodium and chlorine. That's what I want you to know. That's the kind of question I want you to be able to answer about lattice energy, okay? Now, Kevin,
Yeah,
all right, you have your periodic table out.
I do.
All right, look at magnesium and sulfur and compare that to sodium and chlorine. Are they about the same size?
Yeah,
About,
yeah,
I would say probably the magnesium and the sulfur, maybe a little bit smaller, but it's on the same scale, right?
yeah.
Let's look at the charges, Kevin. What's the charge on magnesium?
That +2.
Sulfur?
0.
Sulfur?
I don't know.
Come on, it's right underneath oxygen. What's the charge on oxygen?
I don't know. Negative +1. Well, I don't know.
Somebody help him.
-2.
-2. So we have magnesium at a +2, sulfur at a -2. Let's compare that to sodium and chlorine. What's the charge on chlorine?
Is it -1?
Now chlorine, yes, chlorine's a -1. Sodium.
+1.
So which one has the bigger charge difference? Magnesium sulfur or sodium chloride?
Sodium chloride.
Sodium has a +1, chlorine has a -1. Magnesium has a +2, sulfur has a -2. Which one has the biggest charge difference?
I'm guessing you're saying the magnesium then?
Because we're dealing with +2 and -2, as opposed to +1 and -1.
Oh, okay.
The difference between +1 and -1 is 2. The difference between +2 and -2 is 4. So the charge is greater for the magnesium sulfur. So since the charge is greater for the magnesium sulfur, and since the charges are on top of this equation, the energy, lattice energy for magnesium sulfur, magnesium sulfide is going to be bigger than the lattice energy for sodium chloride. That's what I kind of want you to know about lattice energies, okay? And that's basically what I just went through. Now, when we're dealing with this, I'm going to use a different screen. If we're dealing with energetics, with lattice energy, it takes energy to get the chlorine, to get that separated from one another, to separate the two chlorines from one another, and it takes energy to take that electron away from sodium. If we gain an electron to chlorine, that's exothermic, so the energy goes down. But still, what's happening here is we've started here and there. Overall, that's an energy gain. What happens when the chlorine and the sodium get together is that they attract one another. That involves more release of energy, And that is why overall you get this huge delta heater formation for sodium chloride. Again, nothing more than I've already said. Some of the properties. Ionic substances are hard and brittle. They have high melting points. Ionic substances do not conduct electricity when they're in the solid state, but they do when they're dissolved in water or in a liquid state. So quickly, we're going to get into covalent bonding here. Covalent bonding is involved with the sharing of electrons. Typically, when we're dealing with covalent bondings, we're dealing with one nonmetal linked with another nonmetal. They can be polar or nonpolar, and I'm going to get into those definitions later. Covalent bonding can involve single, double, or triple bonds. What's happening is they share the electrons. Because they're sharing the electrons, this becomes the sticking factor of one atom to another, the glue that keeps one atom bound to another. It's because they're sharing these electrons with one another. But you have to realize there are several factors that are going on here. We have an attraction between electrons and the nucleus. We have repulsions between the electrons, and we have repulsions between the nuclei. The overall energy that's involved here has to coordinate these three factors. When we're dealing with the octet rule, basically what's happening with the octet rule is we're gaining, losing, or sharing electrons in order to achieve a noble gas electron configuration. So if we have one fluorine that has an extra electron out here that's unpaired, and we have another fluorine with another electron that's unpaired, if we put the two of them together and share those two electrons, we get 8 around this fluorine and we get 8 around this fluorine. So both fluorine now have an neon configuration. If we have a single bond, that means we have one pair of electrons that's shared between one atom and the next atom. If we have a double bond, what this means is that we have two pairs of electrons that are shared by both atoms. Designated by 4 electrons between the two atoms for a double bond, 1 pair of electrons for a single bond. So if we have a triple bond, that's going to involve 3 pairs of electrons that are shared. Are we good with this, guys? All right, I'm going to get through Lewis dot structures today. I'm going to get through that. And I'm going to get through at least one example of it. Now, did you do as I asked and copy those pages I asked you, those slides I asked you to copy? If you did, it will be a big aid for you. If you didn't, then I want you to do it for Monday or Tuesday. All right. Valence electrons are the only thing that are important. They're the only electrons that are involved in bonding. So I can represent all the elements by the electronic symbol and 1 dot for each valence electron. So if I have oxygen, oxygen has 6 electrons. When you are putting electrons around an atom, do it singly. So if I'm doing oxygen, I'm putting 1 here, 1 here, one here, one here. That's 4. I have 2 valence electrons left. Once you have 4 sets or 4 individual electrons out, then you have to start pairing them up. So for oxygen, I would pair one more electron with this first electron, another one with this one. Now, remember, we're sharing electrons to make a bond. Okay? If I have a paired up set of electrons, they can't bond with anything because they're happy. Gabe, look at that oxygen atom. Does oxygen have any unpaired electrons?
No.
No? Look at this lone guy up here.
Oh,
Look at this
that's-
lone guy down
That's
there.
part of them. I didn't see those. I just saw the 2 on side by side of O. Well, so it does.
It does. That's how it has how many?
2.
So can oxygen bond with something here?
Yes.
Can it bond with something else down? Can it bond with something else down there?
Yes.
So how many things can bond with oxygen?
2.
Already, this is giving us information. If I have nitrogen and I want to represent a nitrogen atom, 5 valence electrons, I put them in the 4 separate sites first, 1, 2, 3, 4. I put 4 electrons around nitrogen, but I have 1 more. So it has to be paired up. It has to be paired up with one of the original 4. So Cassidy, how many unpaired electrons does nitrogen have?
3,
How many things can bond with nitrogen?
3.
Already, again, we've got information. I'm not going to go here. Similarly, if I am dealing with molecules, I can represent them as well. Because if I put a pair of electrons between 2 atoms, this means that they are sharing the electrons. So if I draw a carbon atom, carbon has 4 valence electrons, which means you put a carbon and 1, 2, 3, 4 electrons out there. So carbon can bond with 4 things. I represent the 4 things that carbon can bond with by putting a pair of electrons between each one of them. So this carbon and this hydrogen are sharing these 2. This carbon and this hydrogen are sharing these 2. So this is how I represent molecules. And we're going to learn how to draw Lewis dot structures. Again, please, on Tuesday, copy these next couple of slides. The rules. You're going to be given a molecular formula. Write down the elements. You're going to write down the elements so the one with the least electronegative element is in the center. Sometimes you can't do that. Like, for example, with H2O, oxygen is more electronegative than hydrogens, but hydrogens can't act as the center of the molecule. So in that case, the oxygen goes in the center. Try to put the most electronegative in the center. Then you're going to add up all the valence electrons and account for charges. If your thing that you're trying to put together, if your ion is has a positive 1, you're going to subtract 1 from all the valence electrons. If your ion that you're trying to draw a Lewis dot structure of has a -2, you're going to add 2 electrons to that, because -2 means you have 2 extra electrons. +1 means you have 1 less electron. So you're going to add up all the valence electrons. Next thing you're going to do is you're going to put 2 dots, 2 electrons between each of the electrons. That accounts for the bonds in the molecule. For each bond, you're going to have 2 electrons. Multiply that by the number of bonds you have. That's the number of bonding electrons that you've already used up. Subtract the bonding electrons from the total valence electrons. Next step, all the terminal atoms. The terminal atoms are the ones at the very end of the molecule. Fill them up with pairs of electrons. Hydrogen's the one exception. Hydrogen can only take 2 electrons, and if it's bonded with something, it has no more lone pairs around it. So you're going to fill the terminal atoms with pairs of electrons. Then these lone pair electrons, you're going to subtract from the remaining electrons. Any leftover electrons get put on the center atom. If the center atom doesn't have 8, as a general rule, take a lone pair from one of the terminal atoms, shove it between the terminal atom and the center atom. You're creating double and triple bonds by doing that. Check your molecule to make sure every atom has 8 electrons around it. So we're going to go through a couple examples of this, depending upon time. Note something though. Halogens, because they have 7 valence electrons, they have only 1 unpaired electron. They can only bond to one other atom. Therefore, they act like an end cap, a plumber's end cap. And plumber, when they're putting pipes through your house, if they want to give you access to putting another faucet or another nozzle, what they will do is they will put an extra pipe above it, but they'll put an end cap, which means for the moment that no more piping is going in that direction. Halogens and hydrogens end the chain of the particular molecule. So if I'm dealing with SO2, I put the least electronegative in the center between sulfur and oxygen. Cassidy, which one is the least electronegative?
Sulfur.
Putting that in the center with the 2 oxygens on either side. Next rule, I add a pair of electrons. Next rule, I add up all the valence electrons. The charge on SO2 is 0, so I don't have to add or subtract electrons from it. Sulfur has 6 valence electrons. There is 1 atom. So there are 6 valence electrons contributed by the sulfur. Oxygen also has 6 valence electrons, but there are 2 of them. So I get 2 times 6 from my oxygens. I have 12. I have a total of 18 valence electrons. Rule 4, put 2 dots between each of the elements. These are the bonds. The reason you have to do that is if you don't have 2 electrons between them, then that atom is not associated with the other atom. So I've got 2 electrons between this sulfur and this oxygen, 2 between this sulfur and this oxygen, 4 bonding electrons. I had 18 valence electrons. So I subtract the bonding electrons away from the 18, 4 from 18, I have 14 left. Next rule, I am going to fill my terminal atoms with pairs of electrons. So this oxygen over here has the 2 electrons that it's bonding with sulfur. It can take 6 more electrons. So I put 2, 4, 6 around this oxygen. Again, this oxygen has 2 electrons it's paired with the sulfur. I put 2, 4, 6 around it. I've now added 12 lone pair electrons, 2, 4, 6, 8, 10, 12 around my terminal atoms. I had 14 left. I just used up 12 of them. So I subtract 12 from 14. I have 2 left. Rule 8, I put those extra 2 around the center atom. I have no more electrons left. Yet I'm looking at my center atom. My center atom only has 2, 4, 6 around it. It needs 8. So what I'm going to do is I'm going to take 2 from one of the oxygen, 2 of the lone pairs from one of the oxygen, shove it between that oxygen and that sulfur. Now, the last step is to check to see that each element has 8 electrons around it. This oxygen has 4 bonding electrons with it, plus 2 lone pairs for 8 electrons. This oxygen has 2 bonding electrons and 6 lone pair electrons. It's happy with 8. This sulfur has 1 bonding between this sulfur and this oxygen, and 4 between this oxygen and itself. So that's 6 bonding electrons plus 1 lone pair electron for 8. Everything is happy. Now, I hate dots. I cannot stand dots, because what eventually happens is when you guys are drawing these dots out here, you smudge one of the dots, and you may smudge 2 of the dots because you're erasing things and things of that nature. So you get smudges, and then I have to interpret them. I interpret them wrongly, and then that gets me in an argument with you. I don't like that. I much prefer lines because lines are less arbitrary than dots. I can represent 1 line for 2 for electron pair. So if I'm going to draw the double bond between this oxygen and this sulfur, I'm going to put 2 lines between that sulfur and oxygen. I have 2 lone pairs. They can be designated by 2 lines. This oxygen has 3 lone pairs, so I'm going to put, this one's supposed to be associated with this. I'm going to put 1, 2, 3 lines to make up for the 3 lone pairs. Are we good with this, guys? I think I have time to go through one now. Do you want to end it there, or do you want me to go through one more example? Are we kind of remembering doing Lewis dots again?
Yeah.
Yeah, I remember it.
Do you want me to go through the other example, or do you want me to? I've got like 2 minutes.
Sure.
Because you said something, Cassidy, you get to help me start it. I got CO2. What goes in the center?
The carbon.
All right. Now, I have to put 2 electrons. Well, I have to count my valence electrons. Kevin, how many valence electrons are there around oxygen?
6.
So I have 2 oxygen atoms. That means I have 12 from oxygen. How many do I have from carbon?
Is it 5?
Nope. Somebody help them.
4.
4. Kevin, if you go over from lithium, lithium 1, beryllium 2, boron 3, bicarbon there are 4, okay? So my total valence electrons are 12 plus 4. I have 16 valence electrons. Okay? Now, Ian, I haven't bothered you yet, Ian.
Right.
My next rule, I have to put 2 electrons between each of the atoms. How
Right.
many does that use up?
4.
4, because I have to put. Sorry. So I'm going to put 2, I'm going to put 1 line between my carbon and oxygen, another line between this carbon and this oxygen. That represents 2 and 2 electrons for 4 electrons. I'm going to subtract that from the normal amount of valence electrons. 16 minus 4 gives me 12 left. Gabe, do you know what the next rule is?
This is the one you have on the screen.
Nope, that's rule 5. Where do I go from here?
Don't you pair them?
I pair them, but I put them around the terminal atoms. This carbon and this oxygen have 1 because of the bonding. I can put 2, 4, 6 more around the oxygen, right, Gabe?
Right.
This carbon and oxygen have 2 electrons. How many more can I put around this terminal oxygen?
6.
So I've used up 6 plus 6. I've used up
That's 12.
12.
Oh, okay.
So do I have any more electrons left?
No.
I have no more electrons left. Yet, damn it. Okay, yet my carbon only has 4 electrons away from it, around it, right? So I have to get 8 around my carbon. Where are those going to come from, Cassidy?
They're going to come from the oxygen.
I'm going to take 1 lone pair, put it in here. I can take another one from the same oxygen and put it in here and make a triple bond. I can do that. Or I can put 1 pair in here and another one from the other oxygen in there. If I do that, I make a molecule that looks like this, or I can make one that looks like this, where the carbon and the oxygens both have double bonds around them, or I can make a molecule where the carbon has a triple bond with one of the oxygens and a single bond with the other one. Is this coming back to you guys?
Yes.
Yeah.
Okay, I'm a little bit over. I went about 3 minutes over. Where we are going to start, and I literally, guys, these are simple molecules. Please try them, practice them, okay? Please try and practice them. Where I am going to go from this, the way I teach intro, I do not disobey the octet rule. In other words, when I'm teaching this in the intro, all the atoms have 8 electrons around it. That is not the case. And we're going to get into that when we deal with exceptions to the octet rule. And that's where we're going to start on Tuesday. Okay? Any questions about Lewis dots? We went through, we talked about the periodic trends that we are dealing with. We went from the periodic trends to, we discussed in the periodic trends, we discussed ionization potential, size, electron affinity, and electronegativity. We went from there to ionic bonding. We learned that in ionic bonding that it takes energy to take an electron away from an atom, And when that electron gets sucked up by another atom, that is exothermic, but it's not enough energy to accommodate what really happens in the reaction. We have to accommodate that by something called lattice energy. And the lattice energy is equal to a constant times the charges divided by the distance between them. Then we went into covalent molecules, and with covalent, we're representing them with Lewis dot structures. Okay, guys, if that's all, then I will see you on Tuesday then.
Thank you. Have a good weekend.
Guys,
Have a good one.
Ian, stay here for a second. Guys, you did as a general rule, you did a great job on the test. Ian, I really meant what I said. I really am proud of you. You kicked ass on that test.
Thank you, Professor.
Okay, if you want to stick around, I'm going back into the periodic trends with Gabe.
Is the next Zoom call at 5:30?
Yes.
Okay, I'll see you at 5:30 then.
Okay. Okay. Kevin, you sticking around?
No, I gotta go to work. Have a good
Okay, I'm
weekend.
sorry about that, Kevin. Okay, Gabe. All right. I'm going to sit and I'm going to. That's not what I want. I don't want that. All right. I'm going to hit home and add a slide. And I'm going to change the layout to this. Okay. All right, Gabe.
Yes.
All right, if I'm drawing an orbital diagram and I'm drawing the S's and the P's,
Right.
why is that doing that? Okay. Okay. Does that make sense to you?
Yes.
Because S has 2 electrons, one going up, one going down. The
right.
P
and
has the P
6.
has 6. All right. Now, if I have this situation, I have a filled S, correct?
Correct.
And I have no P's. So I
Okay.
have a filled orbital.
Mm-hmm.
I'm happy.
I don't
I'm
know.
happy. I have a filled orbital.
Okay, yes.
So if I have a filled orbital or I have a half-filled orbital, I'm happy. So
Okay.
equally here, if I have this,
Mm-hmm.
I'm equally happy, right?
Right.
All right. Now, can you see if I have this electron orbital diagram, would I be happy if I gained another electron?
Yes.
Okay. So I'm happy right now. I've gained that electron. Okay.
Right.
So it's going to take less energy for me to gain an electron and get to this configuration than it does for me to go from this configuration to there. This is not a stable situation. Right, Gabe?
Okay. Right.
Right? So going from adding an electron when I'm in this situation, it's going to take more energy to put that second electron in there. Okay?
Okay.
Now, if I want to put a third electron in there,
Mm-hmm.
because I'm half filling my p orbitals, that's a stable situation, right?
Right.
So it takes less energy, or I gain less energy by accepting an electron going from the first electron in the p's to the second. I get less energy that way than going from having 2 electrons and putting the third in there. Does that make sense to you, Gabe?
Yes. So you're saying if the p orbital it only had 2, or it's happy, but when it has
No,
3, it's
no.
like even more. Oh, it's not happy.
Well, it's not happy because it doesn't have a half-filled shell, half-filled suborbital.
And then when it gets to the third one, it's stable and it's happy. Right?
Yes. All right. Now pull out your periodic table.
Alrighty.
Okay, Gabe, got your periodic table?
Yep.
Right now, we're talking electron affinity, gaining an electron, okay?
Okay.
So if I have carbon,
Mm-hmm.
right?
Right.
Isn't that the electron configuration for the second shell of carbon? Isn't that the orbital diagram?
Yeah. Yes, it is. Yes, it is correct because you have your
Alright.
2s2, 3p,
Two.
2 or
All
4
right,
or 2, 2, 2.
2, okay? So if I'm going to add another electron to this,
Mhm.
right? If
Right.
I'm going to add another electron to this, have I just filled my orbital? Half filled my p suborbital.
Yes.
All right, so it likes that situation. It likes that situation, so a whole lot of energy is going to be generated from that. All right.
Okay. All right.
Now I have nitrogen. Is this nitrogen's electron configuration?
Yes, this is.
So if I want to add another electron for nitrogen, don't I have to put it into one of these orbitals?
What do you mean?
I have nitrogen. This is the electron configuration for nitrogen.
Correct.
If I want to give nitrogen another electron, where's that next electron going to go?
In one of the 2p.
It's going to go
Right.
in like, nope, like that, right?
Right. Well, that wouldn't be nitrogen anymore.
Yes, it would. Remember, what
Right.
defines the atom are the protons, not the electrons.
Okay. Isn't that oxygen's configuration?
That is oxygen's normal configuration. But I'm telling you, I have a nitrogen atom, and I'm forcing that nitrogen atom to gain one more electron. If I force the nitrogen to gain one more electron, I have to put it in one of my suborbitals, right?
Right.
It doesn't like this situation. This is like two brothers being in the back seat. They don't like being that close to one another. So it's not a good situation. So
For nitrogen.
when you add another electron to nitrogen, it is exothermic, but it's not as exothermic as adding an electron to carbon.
Okay.
Is that making sense now, Gabe?
Yeah, that makes a lot more sense.
All right. Now, we've dealt with our electron affinity, right?
Right.
Electron affinity is gaining an electron.
Mm-hmm.
Ionization potential, okay? That is the energy it takes to take an electron away from an element, okay?
Okay.
So we said that this was nitrogen's electron configuration or orbital diagram, correct?
Correct.
Is it happy?
Yes.
So if I take one away, Is it as happy?
No.
It wants to have that third electron. It wants to keep that third electron in there.
Right.
So it's going to take more energy to take that electron away from nitrogen than if I'm talking about oxygen. Because this is oxygens, right?
Right.
Look what happens if I take an electron away from oxygen. Do I not have a half-filled p orbital?
Right. We do.
Oh, all right. Does this make things a little more understandable, Gabe?
Yeah, I just have one question. Here, I'll turn on my camera so it's not so you can actually see me instead of
Okay.
just talking
That's
to a block. All right, I have one question though. So let's say we do carbons. Can you do carbons electron configuration real fast? So okay, so the p orbital is like half filled. You know what I mean? Or it's 2/3 filled. There's not
It's only
right.
half filled and full.
Okay, so this would still be happy, right? Or like
Relatively speaking.
okay.
All right. But remember, if I'm trying to remember the general trend. What we're talking about right now are the anomalies going from left to right. Normally, when you go from left to right, you have more protons. As you go further to the right, it gets harder to take an electron away. That's the general trend, going left to right, because you have more protons. Okay?
Okay.
Now, what we're talking about are specific areas between nitrogen and oxygen when I'm dealing with ionization potential, because nitrogen's happy.
Mm-hmm.
Oxygen can easily get rid of that extra electron and be happy. So it takes less energy for oxygen to lose its electron than it does for nitrogen. So the ionization potential for oxygen goes down. Remember, as we're going from left to right, it's supposed to be harder to take an electron away from an atom. That's the general trend.
Right.
But remember, oxygen is to the right of nitrogen on the periodic table. So it should take more energy to take that electron away from oxygen. But it doesn't, because I can easily half fill a shell if I take one electron away from oxygen.
Okay, that makes a lot more sense.
All right. Same thing happens. We're going to deal with S shells going to P's, right? Say I have boron.
Okay.
That is the electron configuration of boron, right?
Right.
If I'm dealing with ionization potentials where I'm taking an electron away, if I take this electron away from boron, is it happy?
Yes.
Okay. So it's happy. On the other hand, if this is magnesium, I'm sorry, yeah, that's magnesium. Magnesium has 2 electrons in its 3s orbital. Is it happy, relatively speaking, right now? Does it have a filled shell?
Yes.
Okay. So is it going to, if you try and take that electron away, is it going to be happy that you're messing with its full shell?
No way.
Okay. So it's not going to be happy. So the ionization potential for magnesium is going to be greater than that for aluminum, which is, sorry.
No, you're fine.
This. Okay.
Right.
You see, if I take one electron away from aluminum, I've got a full shell, so I'm happy
Right. That's
if
for
I-
aluminum.
for
Right.
aluminum. But if I
Oh,
compare,
but
if I'm comparing that to magnesium, this is
it's
magnesium.
unstable.
If I take an electron away from magnesium, I'm disrupting a full orbital.
Okay, I understand. So it's all you basically have to compare it between the elements.
Yes,
I mean,
that's
if
what
that
we're
makes
doing.
sense.
We're
Oh
using,
my, okay.
we're using quantum mechanics to explain real phenomena.
Okay,
Okay.
that makes so much more sense.
What I'm trying to say is, if I'm looking at this in real time, I measure the ionization potential for aluminum.
Mhm.
Okay. My ionization, it takes less energy to take the electron away from aluminum than it does for magnesium. And the reason we can explain that is magnesium has a full shell. It's going to take more energy to disrupt a full shell than it does to take one away from the p orbital.
Okay,
All right. Now,
that makes
if I'm
so much sense.
if I'm dealing with electron affinity, remember electron affinity, I'm adding an electron. Okay.
Okay.
So if I have magnesium and I try and add an electron, yeah, okay, I can accept an electron,
Hmm.
but is that a real stable situation? I've got this one electron in the p orbital.
No.
No. So it'll accept it and it'll be exothermic. But if I have, say, sodium that has one electron, doesn't it really want to get another electron to fill that orbital?
Hmm.
So it's going to be sodium gaining an electron. It's going to be more exothermic than magnesium gaining an electron.
Okay,
Is this making sense, Gabe?
that makes a lot of sense.
Good, 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 good.
Okay.
Do you want to go over your test?
I'm actually I should be in a math class right now.
Sorry, Gabe.
But no, bro, you're fine. I have like a 98 in this class, so I can skip. Actually,
No,
could
no.
we?
It's
Or-
Gabe, it's up to you. I'll offer you the same thing at 5 o'clock. I can get into my class early at 5. Would you rather do that?
I'm at work then,
So you'd rather go through it now?
if that's okay with you. Yeah, I mean,
That's fine by me.
Okay. I can. Would you want me to pull it up or screen share?
No, I'm going to screen share it in a second.
Okay.
Oh, crap. What I'm going to do is I'm going to